So friends, we are going to discuss the P block elements and especially the group 18 today. Group 18, especially as we all know, is known as inert gas elements. So we'll start with very basic and then we'll go up to an extent that is required for you to appear in your examinations. While focusing on the group 18 elements, we are very clear with few things that includes the names, that is helium, neon, argon, krypton, xenon, radon, and from this time we are going to learn a new element, that is agneson. Now friends, these elements which are the point of our discussion for the topic, where the P block elements group 18 is under our surveillance of discussion, involves the very first thing for all these elements, and that is its electronic configuration. Remember, we have called them inert gases, and henceforth their general electronic configuration is Ns2np6, which makes a total of 8 electrons. You might be aware very well that these numbers on the top are the number of electrons, and when it comes to 8, it is completion of an octet. Hence, completely filled octet elements are fundamentally called inert gases, and these are the element of group 18. Mind well, although whatever be their electronic configuration at the initial stage, but they will always end up writing Ns2 and P6. If we write for helium, it will be 1s2. If we write for neon, it will be 2s2 2p6. I'm not mentioning the inert gases, 3s2 3p6, 4s2 4p6, 5s2 5p6, 6s2 6p6, and 7s2 7p6. So these are the electronic configurations of the noble gases or the inert gas elements. Now, focusing on few of its important points, we all know that group 18 elements consist of helium, neon, argon, krypton, xenon, radon, and agneson. All these gases are chemically unreactive because of their completely filled shells. They form very few compounds being inert, and hence they are termed as noble gases. If we discuss about the occurrence of these elements, we can very well divide these elements into two parts. That is, element helium, neon, argon, krypton, and xenon are those elements which are naturally obtained from atmosphere in some or other composition. That is 1%, 2%, 3%, we'll just now see in the reference. But element radon and element agneson are obtained through radioactive series decay. What do we mean by radioactive series decay? There are few reactions which emit alpha particles, beta particles, gamma particles. And once these particles are emitted out from a parent element, they result into either radon or agneson. This can be seen over here. All these gases except radon and agneson occur in atmosphere. So these two are not available directly in atmosphere. Their atmosphere abundance in dry air is around 1% by volume, of which, very well important question, argon is one of the major constituent available. Helium and sometimes neon are found in minerals of radioactive origin. Which are these radioactive origin minerals? They consist of pitchblende, monazite, clavite, etc. Now, let us see two reactions which will help us in obtaining radon and agneson respectively. Remember very well, beta. There are few radioactive decay series available. You will study in detail at a later stage. You will come to know 4n, 4n plus 1, 4n plus 2, and 4n plus 3 are the name of these radioactive decay series. Over here, Let us have an element called radium, which is having its atomic number 88 and its atomic mass is 226. If you remember your lower standards chemistry, you will be aware of a term called ZXA, where Z is the atomic number and A is the atomic mass. Now, sticking to this atomic number and atomic mass, when a element radium having atomic number 88 and atomic mass 226 undergoes a decay reaction, it is very clear that it must emit either an alpha particle or a beta particle or gamma particle or radiations or energy, something like this. Over here, it is very clearly seen that it eliminates an helium atom. Now, remember very well, a helium atom which is removed out is nothing but is equivalent to an alpha particle, because one alpha particle is equal to an atom of helium. So, sticking to these words that an alpha particle is equal to an atom of helium, if radium emits helium, then according to a simple mathematical funda, if it is 88 over here on the left hand side, after the reaction arrow, the total has to be 88. If 2 are gone beta, we are left with 86. So 86 plus 2, 88. So from radium, if helium is removed, then element number 86 is radon and we come up with radon. Always remember ZXA, where Z was number of proton, it was also atomic number. So यदि आपके पास 88 atomic number वाला radium है और उसमें से एक alpha particle दूर होता है, मतलब 2 atomic number, you are obviously left with 86, and that 86 is nothing else but radon. So remember very well, this is how we come to a point where from we get our first group 18 element which is not available rather naturally. Coming forward, now we are going to learn argneson, that is one of the newest element of group 18 having atomic number 180. It's a very beautiful reaction where you, if focus, you have 98 californium 249. Remember very well, this 249 is the atomic mass of californium, whereas this 98 is the atomic number of californium. When it reacts with 20 calcium, generally beta, you people have seen 20 calcium 40, but it has an exceptionally obtained isotope which is 20 calcium 48, and when this undergoes a reaction, first of all, three neutrons are removed. Now the question comes, how to write neutron? Neutron can be written as 0 and 1, because the lower number Z represents P, but the upper number A represents both P plus N. If P is 0, then the above number is N and N is 1 neutron. We have 3, so we will have 3 over here 3 times. So 98 plus 20, it makes a sense, that is 118. 118 is argneson. 249 plus 48, a simple mathematics to be undertaken. 9 and 8, it is 17, 9, so it is somewhat around 297. But of these 297, we have 3 neutrons coming out. So 0 and 1 3 times. So 0 and 1 plus 0 and 1 plus 0 and 1. So it will be 3 neutrons going apart. So 3 will be subtracted from this 297 and you will end with 294. So this is how, when it comes to the occurrence of noble gases, or when it comes to its generation, you could very well define from this stanza in your book and this explanation over here on the paper that element helium, neon, argon, krypton and xenon are readily available in atmosphere in some or other content, 1%, a half percent of something like this, whereof argon is in major content. But there are two elements, that is radon and argneson, which are not available directly, hence they are obtained by different radioactive decay series or radioactive reactions, wherefrom when you undertake radium and you remove a molecule of helium, that is an alpha particle, you end up with radon. Similarly, when you have 98 californium reacting with 20 calcium, you end up with argneson and neutron are emitted. So friends, this was our first part. Kindly After every explanation, go through your reference from where you will be reading and learning new words, and this could help you to ask me doubts whenever required. Please make now a habit of learning through online modules because we don't know for how much time we would have to be at home and work to support our government. But moving forward in the same direction, if we want to learn more about this newly discovered element, Agneson, we have already seen some things, but let us revise it by writing that Og is the elemental symbol for Agneson, and therefore it has its atomic number to be 118 and its atomic mass to be 294. Apart from this, if you look for its electronic configuration, we already had made a generalization that Ns2np6. If we start from helium, it was 2, neon it was 3, argon it was 4, krypton it was 5, xenon it was 6, and radon it was 7. So yes, very well said. It is 7s2, 7p6. But if you remember little chemistry of your lower standard, we always have made a generalization that if it is Ns2np6, it has to be n minus 1d and n minus 2f with possibility of maximum electrons, that is 10 and 14. If you consider over here n is equal to 7, then it has to be 6d10 and it has to be 5f14. So this is the basic electronic configuration of Agneson, and never forget to write over here the nearest octet element, or rather to say the inert element, that is radon. So if I write the electronic configuration completely, I must write that Agneson with an atomic number 118 has radon followed by 5f14, 6d10, 7s2 and 7p6. And if you sum up, it will always reach to 118. Let us check. 86 plus 14, it is 100. 110, 16 plus 2, 18. So we are complete in the electronic configuration of Agneson. Only a very small amount of Agneson has been produced. Its half-life is 0.7 milliseconds. You can imagine if you take a gram of Agneson, luckily in your hand, after every zero point 0.7 milliseconds, it will disintegrate into one half. It is very difficult to collect it. It is very difficult to produce it. And if you cannot produce, you cannot collect, you cannot study it, how would you be able to predict its physical and chemical properties? So in the table or in the literature followed in your reference, you will not find any data as of now on Agneson. Except for Agneson, important atomic and physical properties of other elements of group 18 along with their electronic configurations are depicted in the table below, and our first task is to completely learn such type of tables. If you look into very carefully, we will for group 18 first of learn few of its physical properties. What physical properties as of now we are interested in? We are as of now interested in atomic mass, atomic radii, ionic radii, ionization enthalpy, electron gain enthalpy, delta EGH, delta, it stands for density. Let us first focus on these six things. Very soon after, we will be focusing on boiling point, and just after that, we will be focusing on melting point. So friends, keeping our mind intact to all these points, we will be discussing in details each of this component of the physical property of the inert gases. See, you are here to learn the trends. So when I say moving down the group 18, remember very well, moving down the group 18, I mean to say that we are coming from helium, neon, argon, krypton, xenon, radon. So always remember our track: helium, neon, argon, krypton, xenon, radon. Don't write Agneson over here because we are not yet known with the physical and chemical properties of Agneson. So friends, helium, neon, argon, krypton, xenon, radon. We will start with atomic mass. Coming down the group, the atomic mass constantly increases. You can see even in the table, Atomic mass of helium is 4. From there you go to 20 to 39.95. Krypton is 83. Xenon is 131. And radon is 222. And we very well know that is red X A. A relates to proton plus neutron. As we go down the group, the number of proton and neutron keeps on increasing, resulting into increase of the atomic mass. Atomic mass trend, you can directly project this as increasing. We very well know, coming down the group, every time the shell increased. If you remember the paper that was lying here before, and it was very well written, 1s2, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. What I mean by writing this? I very well mean by writing this that every time I am knowing that I am increasing an orbit with an increase in the element in the inert group. And when we know that you are moving away from the nuclei each and every time, the internuclear distance, that is the distance from your nuclei, the electron in the outermost orbit keeps on increasing. And when this increases completely, we can very well say that the atomic radii has increased. So friends, atomic radii also increase as you go down the group 18, that is from helium to neon to argon to krypton to xenon to radon. We can very well say that the atomic radii has increased. Now remember very well, generally there is a trend in chemistry that whenever you discuss atomic radii, you are supposed to discuss ionic radii. Over here, this is an inert group. It has completely filled octet. It is very difficult to either remove an electron or to add an electron. Although it is difficult to remove an electron or to add an electron, although it if removes an electron or adds an electron, it becomes an ion. And when it becomes an ion, we are supposed to study its ionic radii. And the ionic radii follows the same trend as atomic radii. It increases from top to bottom. Coming to an important point, ionization enthalpy. What is this ionization enthalpy? We know that when an atom is in its gaseous state and we are interested in removing an electron from its outermost shell, we need to provide energy. We also know that as the size of an atom increases, the attraction of the nuclei with the electron in the outermost shell decreases. And therefore, you require very minimum energy to remove that electron sitting in the outermost orbit. Over here, if you go down the group, that is from helium to neon to argon to krypton to xenon to radon, you very well know that the quantum number, main quantum number n, principal quantum number n is increasing, the shell keeps on increasing, and hence the attraction decreases. And therefore, you require lesser energy to break that electron and throw it out in its gaseous state. Over here, keeping that concept in mind, if we come down from helium to neon to argon to krypton to xenon to radon, as the size increases, it becomes very easy to throw out an electron, and hence we require lesser energy to do that. And when you require lesser energy to do that, ionization energy decreases. So, friends, you can check all these values on the screen because we have mentioned them in the table. It is helium with 2300, neon with 20, 1500 with argon, krypton with 1300, xenon with 1100, and radon with 1037. So friends, you are very well able to see that the values are keeping on going down with the increasing shell because the attraction is decreasing. So as of now, we have learned that the atomic mass is increasing going down the group. Atomic radii is increasing going down the group. Ionic radii tends to increase going down the group. But when it comes to ionization enthalpy, the order gets reversed. Going down the group, its value decreases. For a while, let us consider electron gain enthalpy. As we are just learning the trends, I won't go in much detail with the electron gain enthalpy. But remember very well, whenever an atom has an octet filled completely, it does not require to gain an electron or to lose an electron. We call it inert. Although, if you try to give it an electron, it is very difficult for it to gain that. Henceforth, you also need to provide energy along with that electron if you wish that atom being inert takes the electron provided by you. So always for inert gas elements and generally for atoms or elements not easily accepting electrons, electron gain enthalpy is always positive. Otherwise, we know that electron gain enthalpy values are negative, and we will learn that in the group 17 of the same content p block elements. But as of now, Remember that the electron gain enthalpy are generally negative, but when it comes to inert gases or the elements which do not easily accept electrons, the electron gain enthalpy always becomes positive. And over here, keeping this concept of electron gain enthalpy to be always positive, the order of increasing value of positiveness is helium is the least, followed by radon, then after it comes to xenon. After xenon, it comes to argon and krypton. And after argon and krypton, it comes to neon. So this order, helium to radon, radon to xenon, xenon to argon, argon to krypton, and from krypton it directly jumps to neon. This is an increasing order in the positive values of the electron gain enthalpy of the group 18 elements. Now, coming to another important concept, and that concept is density. Friends, be very clear when it comes to density. We have a very simple mathematical equation, that is density is equal to weight by volume. More the increase in weight, generally there is a more increase in density. And we have already studied in this table where from we initiated that coming down the group, the atomic mass increases. If this weight or mass rather to say increase, density is directly proportional to it and hence it has to increase. So density increases with the increase in weight. So over here you can see the values initially are 10 to the power minus 4 and then gradually it becomes 10 to the power 3, and we know very well that 10 to the power minus 4 is smaller, 10 to the power minus 3 is larger, and henceforth we can say that coming down the group in 18, density increases because their weight increases, and in the formula density is directly proportional to weight. Now, two important points, that is melting point and boiling point, with no exceptional values. For group 18, melting point and boiling point jointly increases going down the group. Friends, remember very well that atomic mass, atomic radii, ionic radii, density, melting point and boiling point in group 18 from helium to radon increases flat. When it comes to electron gain enthalpy, you have exceptional values. So remember those exceptional values very well. When it comes to these points, be very clear with what you are learning. So these are few of the physical properties that must be discussed when we are learning group 18. I hope you are getting clear with what I was speaking in this topic. Nevertheless, if you find any queries, there my number as well as my email ID is getting flashed. You can contact me anytime for any online help during this period of lockdown, and even after that, you can contact me via mobile or via my email address for any of your queries. Friends, it is a two-way learning process. So I won't be reading this each line which already I have discussed, although I'll be making your attention very clear to few points which, if not discussed, need to be discussed as a part of my duty. Coming to this point of physical properties, I'm leaving few part apart. You can learn by yourself, that is electronic configuration, ionization enthalpy, atomic radii, and electron gain enthalpy, that has already been discussed over here. But coming to physical properties, all these noble gases are monoatomic. They are colorless, odorless, and tasteless. They are sparingly soluble in water. They have a very low melting and boiling point because the only type of interatomic attraction in these elements is a weak dispersion force. And you know that weak dispersion forces are very weak, so you require very less energy to break them, and you can easily break them. It has an unusual property of diffusing through most of the commonly used materials like rubber, glass, or plastic. So it is very difficult to hold them or to collect them or to store them. So friends, probably up to my knowledge, this was the first part of my discussion, which involved the electronic configuration of the noble gases, its atmospheric abundance, its method of obtaining for this non-natural radon, and rather to say augneson. I'm using the word non-natural purposefully because you need a chemical reaction to perform. There are some details of augneson because it was coming for the first time. A table which could explain all the physical properties which even could not be explained by these four statements completely, followed by few physical properties where I should draw your attention. Now we will be coming to chemical properties in the very next part, which is going to be after this in a continuation. But as we know that we require smaller videos to upload it very well, I am stopping this first part over here where I have tried to cover the initial part of group 18 of the P block, and in these two sheets, if you find any query, you can contact me anytime, and stay tuned for the second part where I'll be continuing after the physical properties, that is chemical properties. Thank you.